to Unity Space Travels. Today you have chosen the complete black hole experience. So just sit back, relax, and allow my voice to guide you through space. Imagine a giant cloud in space, cold, dark, and made mostly of hydrogen and helium, the two simplest elements in our universe. Gravity in space starts to pull the gas together. Over millions of years, the cloud contracts. As it shrinks, the gas particles smash closer and closer together. And where does that gravity come from? Well, it comes from the mass of the gas and dust itself. Every particle, no matter how small, has a gravitational pull. That is what Newton's universal law of gravitation tells us. In these giant clouds where stars form, gravitational attraction between particles causes clumps to grow. As some regions become denser, their gravitational attraction strengthens, pulling in even more material and triggering a runaway collapse. This crushing pressure makes the gas hotter and hotter until something amazing happens. At the very center now, where it's hottest and densest, nuclear fusion begins. Fusion is the process where two light atomic nuclei combine into heavier nucleus, releasing enormous energy. Hydrogen atoms are made of just one proton, so it takes relatively little energy to push two of them together compared to heavier atoms. Now you know that when stars are young, they are mostly made of hydrogen gas. And in the star's core, where it's hottest and densest, hydrogen nuclei move fast enough to overcome their electrical repulsion and they fuse together. This fusion of hydrogen atoms forms a new element, helium, and crucially releases energy while doing so. According to Einstein's famous equation, E equals mc squared, the energy released in that moment pushes outward against gravity, keeping the star stable. It produces the star's light and heat, and it allows the star to shine for billions of years. So, fusion, basically just means that hydrogen atoms are slamming together so hard that they combine into helium atoms. And when that happens, a little bit of mass gets turned into a lot of energy. Energy that pushes outward, balancing the pull of gravity inwards. Growing steadily with all the energy created by fusion inside. A yellow or red main sequence star is born. Stable main sequence stars, such as our own Sun, maintain equilibrium by producing energy through nuclear fusion in their cores. The ability to generate energy by fusion defines a star. A star on the main sequence shines steadily for millions or even billions of years, as long as it has hydrogen to fuse in its core. Hydrogen fusion releases a steady stream of energy that balances gravity's inward pull. Now you know that fusion depends on hydrogen fuel. And when the hydrogen runs out, well, the star loses its main way of pushing back against gravity. Without fusion, there is no longer enough outward pressure to balance it. So, gravity wins, and the core begins to shrink under its own weight. As it contracts, the core compresses and heats up even more. Compressing a gas increases its temperature. That's a basic principle from thermodynamics. However, even though the core is heating up, it cannot immediately start new fusion, because now, without hydrogen, the core is mostly helium. Only helium is left there after the hydrogen has run out. And helium atoms require much higher temperatures to fuse. Meanwhile, something interesting happens to the outer layers of the star. Instead of collapsing along with the core, they expand outwards. This expansion happens because as the core contracts and becomes hotter, it releases huge amount of energy. This energy radiates outwards and heats the surrounding layers of gas, causing them to expand. And even though the star grows much larger, its surface becomes cooler, because the energy is now spread out over a vastly graded area. As the star expands and the surface spreads out, it cools down and it actually turns redder in color. It can swell up to hundreds of times its original size. The star has officially left the main sequence and becomes a red giant. An enormous, bright, but relatively cool star. This entire transformation, the shrinking core, the expanding outer layers, it's a natural consequence of the physics inside the star. And it can happen over millions to hundreds of millions of years. As almost all the hydrogen is used up and the core is shrinking, eventually the core reaches a critical point. Temperatures soar to about 100 million Kelvin, and the star is finally hot enough to start helium fusion. This ignition, as opposed to hydrogen fusion, helium fusion is sudden and dramatic, especially in stars similar in size to the Sun. This is called the helium flash, a rapid, powerful burst where helium nuclei, which each have 2 protons, collide and fuse into even heavier elements like carbon and oxygen. This new fusion process is known as the triple alpha process. After the helium flash, the structure of the star changes. Instead of fusing hydrogen in the center, helium fusion now occurs in the core, while hydrogen fusion continues in a very thin shell around the core. This gives the star a new but temporary source of energy, and the star stabilizes for a while. This marks a new phase of the star's life, one that will last until the helium fuel in the core is exhausted too. This new phase is stable for a while, but not forever. As a star nears the end of its life, the path it follows depends entirely on its mass. If the star is, let's say, about the mass of our sun or just a little bigger, a low mass star, the story is relatively peaceful. Once the helium in the core is exhausted, the star cannot reach the extreme temperatures needed to fuse anything else, anything heavier. Without a new fuel source, gravity takes over. The core now made mostly of carbon and oxygen, contracts and becomes incredibly dense and hot. But it never ignites new fusion. The star actually sheds its outer layers into space, forming a glowing shell of gas known as a planetary nebula. Over time, the material from the planetary nebulae enriches the galaxy, helping to seed the information of new stars and planets. What's left behind at the center? It's a white dwarf, a tiny Earth-sized remnant with about half the mass of the Sun. A white dwarf doesn't explode or collapse further. Instead, it is held up by a strange quantum force. It is called the electron degeneracy pressure, a phenomenon that just resists further compression. Over billions of years, the white dwarf will gradually cool and fade, becoming a cold, dark ember floating quietly through space. This is the final chapter of a low-mass star. So, what about massive stars? Those with much greater mass than the Sun. For massive stars, the story is far more dramatic. After hydrogen, helium is used up, the immense gravity and pressure inside these giants is still strong enough to ignite new stages of fusion. Helium fuses into carbon, carbon fuses into oxygen, oxygen fuses into neon, neon into magnesium and silicon, and finally, silicon into iron. Inside, the star builds a layered structure that looks like an enormous burning onion. Each shell around the core fusing a different element at the same time. The star burns through these fuels faster and faster, racing toward its final collapse. But iron changes everything. For millions of years, the star has found ways to keep its balance, fusing lighter elements and releasing the energy that is pushed outward, balancing the star. Iron, however, breaks that cycle. When iron nuclei are forced together, they actually do not release energy. They absorb it. Instead of supporting the star, iron fusion robs it of the very energy that it needs to survive. The moment that the core is filled with iron, there's no more outward pressure to hold back gravity. The star, after a lifetime of fighting collapse, finally gives away. The core begins to collapse inward, falling faster and faster in less than a second. The heart of the star shrinks into a tiny, unimaginably dense ball. The collapse is so violent that even the laws of physics strain under the pressure. As this iron core collapses, the outer layers of the star, still falling inward, slam into the dense core and rebound violently outward. This rebound creates a massive shock wave that blasts the star apart in a titanic explosion. This explosion is known as a supernova. For a brief moment, the dying star shines brighter than an entire galaxy, releasing more energy in a few seconds than our sun will emit across its entire lifetime. And within that explosion, something else happens. The intense heat and pressure forge elements heavier than iron: gold, platinum, uranium, the rarest materials in the universe. These newly created elements after a supernova are hurled into space, seeding future generations of stars, planets, and even life itself. The death of a massive star is not just an end, it's a beginning. It is how the raw materials for everything we know are made. And what happens after a supernova? Well, depending on how much mass remains after the explosion, the story takes its final but most extreme turn. If the collapse core is heavy but not too massive, it stabilizes as a neutron star, a dense, city-sized sphere made almost entirely of neutrons. So compact that a single teaspoon of it would weigh billions of tons. But if the core is massive, Not even the neutrons can hold back gravity. The collapse continues, unstoppable, crushing matter into a single point of infinite density. A place where the known laws of physics break down. And what is born is a black hole. In that moment, the dying star tears a hole in the very fabric of space and time. A region forms where gravity is so strong that nothing, not even light, can escape. The boundary of this region, the event horizon, marks the point of no return. From this moment forward, the story of our star becomes the story of a black hole. One of the most mysterious and powerful objects in the universe. When a black hole is born, something extraordinary happens, not just to the star, but to the very fabric of the universe itself. For centuries, gravity was understood through the ideas of Isaac Newton, a force pulling masses toward one another. But black holes reveal that gravity is not just a force. It is a bending, a warping of the very fabric of space and time. This deeper understanding comes from Albert Einstein's theory of general relativity. According to Einstein, mass tells space how to curve, and curved space tells objects how to move. The greater the mass, the greater the distortion. Gravity is not a force in the traditional sense. It is the curvature of space and time itself. What physicists call spacetime. Spacetime. Mass bends space-time, and objects move along the curves. And when enough mass is packed into a small enough volume, the bending becomes so extreme that it creates a tear in the fabric of the universe. The result is a black hole, a region where space-time is curved infinitely, where the familiar rules of cause and effect, of up and down, of past and future begin to dissolve. At the heart of every black hole lies the singularity, a point of infinite density where our current understanding of physics simply breaks down. Around it forms the event horizon, an invisible boundary that marks the point of no return. The event horizon is not made of matter or light. Is pure geometry, a property of spacetime itself. If you were to fall toward a black hole, you would notice nothing particularly unusual as you cross the event horizon. No sudden jolt, no flash of light. Outside the event horizon, space and time are stretched and twisted in ways that defy everyday experience. Time itself slows down the closer you get to the horizon. Light, trying to climb away from the black hole, becomes stretched and weakened because of the immense gravity inside, shifting into longer and longer wavelengths. This slowing of time is not just a trick of perspective. It is a real physical effect predicted by Einstein's theory, confirmed by observation, and fundamental to how black holes shape the cosmos. The closer you get to a black hole, the more time dilates. From a distance, the black hole appears simple, a dark, featureless sphere surrounded by disordered starlight. But the simplicity is an illusion. Near a black hole, space is stretched to the breaking point, and time itself slows down to almost a stop. A black hole, then, is more than just a collapsed star. It is a scar on the universe, a place where the rules we know, the familiar laws of physics, break apart. It is a region where our understanding of gravity, space, and time is pushed to their absolute limits. And from here, the story of black holes only becomes weirder. Let's say you were to approach a black hole, not just observe it from a safe distance, but actually fall toward it. Your experience would become something both amazing and terrifying. As you get close to the event horizon, you would feel gravity's power in a way that is different from ordinary experience. Gravity pulls more strongly on objects that are closer to its source. Near a black hole, this difference becomes extreme. If you fell in feet first, the pull on your feet would be vastly stronger than the pull on your head. The result is a process scientists call spaghettification. the ultimate cosmic stretching. You would be stretched out, long and thin, into a stream of atoms. The forces would tear you apart, cell by cell, molecule by molecule, until you became a filament of matter, spiraling into the darkness. It is one of the most violent and unforgiving things nature could do. If somehow you could survive the tidal forces, if there were some hypothetical way to endure the fall beyond the event horizon, what would you find? At the heart of the black hole lies the Singularity, a place where all the mass of the collapsed star has been squeezed into an infinitely small point. Here, the known laws of physics cease to function. Our equations don't work anymore. General relativity, the theory that so beautifully describes the dance of planets and the warping of galaxies, can no longer predict what happens. Space and time themselves seem to unravel. Gravity becomes infinite, and meaning, at least as we understand it, dissolves. For much of the 20th century, black holes were thought to be eternal. Once a black hole formed, it seemed that nothing could ever escape it, and it would persist forever. A dark, perfect prison from which not even time itself could claw its way back. But then came a profound idea from one of the greatest scientific minds of our age. In the 1970s, Stephen Hawking showed that black holes are not entirely black. According to the strange and beautiful rules of quantum mechanics, black holes can emit radiation. Tiny quantum fluctuations at the edge of the event horizon create pairs of particles. One might fall inward and the other one escapes outward. To a distant observer, it appears as though the black hole is glowing, releasing energy back into the universe. This radiation, now known as Hawking radiation, means that black holes are actually not immortal. Given enough time, far longer than the current age of the universe, a black hole might gradually lose mass, shrink, and perhaps even evaporate entirely. Black holes are now understood to be finite, objects that, over eons, are destined to disappear. But Hawking's insight revealed something even deeper and far more troubling: the black hole information paradox. In the laws of quantum mechanics, information, the precise description of the state of matter, can never be destroyed. Yet, if a black hole evaporates away completely, it seems that all the information about what fell in it, the stars, the planets, the atoms, would be lost forever. This posed a very scary question. If black holes erase information, does that mean the fundamental rules of the universe are incorrect? Or is the information somehow hidden, encoded in the radiation itself, locked into the fabric of spacetime in ways we just don't understand yet? Decades later, this paradox remains one of the most profound mysteries in physics. It touches the heart of two towering theories: quantum mechanics and general relativity. And it shows us that somehow our current understanding of the universe is incomplete. And then there's the singularity itself. At the center of every black hole, our equations predict a point of infinite density, infinite curvature, the singularity. But infinites in physics are often a sign that our theories have reached their limit, a warning that we need something more. A quantum theory of gravity, a deeper framework that can describe not just the large scales of planets and stars, but the tiny, twisted geometry inside black holes. Modern theories, from string theory to loop quantum gravity, offer glimpses of what might lie beyond the singularity. Perhaps a bridge to another region of space? Perhaps another dimension? We do not know what truly happens at the singularity. It lies beyond the reach of science as we know it. A place where quantum mechanics and gravity collide, and where a new theory, one uniting the small and the large, will one day be needed to fully explain the truth hidden inside of a black hole.